So yesterday we did not get to do a four-sided die example on 6.6. So let's suppose we roll a four-sided die. If the result is a 1 or a 2, we roll again. Otherwise, we stop. So if we get a 3 or a 4, we're going to just stop. What's the probability that the total of our rolls, whether it's 1 roll or 2 rolls, is at least 4? So like if we landed on a 3 and a 2, add it together, that's 5. 5 is bigger than 4. That's what we want to find the probability of. So let me take a screenshot of this. We'll work it together, and then we'll be good to go. Okay. And then while I'm setting this up, dual credit, you'll need your calculators out today. Okay. You get an Inspire? Yeah. I'm not going to show you all the steps on the Inspire, but you're more than welcome to.
One question before we get back to fund start.
Sure.
I'm on the last one. Maybe you should a compliment, an idea. Yeah, you just don't know.
Hopefully we'll get through before 2 and I'll be able to. I'll send you a message.
All right, thank you, I appreciate it.
Okay, so four-sided die. Let's think of all of our possibilities here. So it gives us a whole paragraph, but if you're like me, you read that paragraph and you're like, yeah, sure, yeah, whatever. This makes as much sense as trying to look through mud does. So that's why I didn't copy the paragraph over. We're just gonna reason through it ourselves. So we're going to say that A1. We're going to say that A1 is the event that we roll a 1 first. Now, what happens if I roll a 1? Do I roll again or do I stop? It says we roll once more. So if I roll a 1, I'll have to roll again, which means I can get another 1. I can roll again and get a 2. Roll again and get a 3. Or roll again and get a 4. So let me preface this by saying that B is the event that the sum is 4 or more. Okay, so if I roll a 1 first, then I'll have to roll again. Of my rolls, again, which one gives me 4 or more as the sum?
Third one and the fourth one.
These, right? So I can say the probability of B given A1 would be equal to what? 0.5. That's right, 1/2. Okay, let's look at A2. So A2, we roll a 2 first. So now, if I roll a 2 first, what happens? Do I stop or keep going? Keep going, so I gotta roll again. So my options here, I could get a 2 and a 1, 2 and 2, 2 and 3, or a 2 and 4. I hope I hit record. I thought I did. Now I'm like getting paranoid that I didn't, since I didn't record the other day. Okay, nope, I'm recording. Good. Okay, which ones of these gives us a sum of 4 or more?
75%.
75% of them, right?
75.
So the probability of B given A2 is 3/4, or you could say 0.75. A3 is where we roll a 3 first. Now, what happens if I roll a 3 first?
100% of them you get 4 more.
100% I get 4 or more?
Yeah.
Do I roll again if I get a 3? I don't get to roll again. So
Oh, what is it?
it says,
I didn't read that rule, my bad.
so we just get a 3 over here, and that's it. So the probability that B occurs given A3 is 0.
Oh, that's shifty.
And then we have A4. We roll a 4 first.
That'd be 100%.
I roll a 4. What's the probability that B occurs? Given I get a 4? 1. It's guaranteed to occur. Okay, so if I want the probability that B occurs, I would have to do the probability that B given A1 occurred times the probability of A1 plus probability of B given A2 occurred times the probability of A2. All the way down to, which I'm really only leaving 1 out, but still. I'm running out of room, so 4 times the probability of A4. Now, what are each of these individual, like A1? So what's the probability we roll a 1? 1/4, right? So we plug this in. B given A1, we said was 1/2. So it'd be 1/2 times 1/4. B given A2 is 3/4. So 3/4 times 1/4. B given A3 is 0 times 1/4. Plus B given A4 is 1 times 1/4. And then if we add all of those up, what's the probability that our sum is 4 or more? Point 0.5625, that's right. Questions on this example? Okay, so let's move on then to section 6.7. So 6.7 is estimating probabilities empirically using simulation. So sometimes we're not able to either estimate it or to determine them analytically or observe. I mean, sometimes we just can't do it. So simulation provides a means of estimating probabilities when we're unable to determine them analytically, or it's impractical to estimate them empirically by observation. So the example we're going to talk about, just to kind of give you a little bit of a foreshadowing, we're going to look at how the population would change if couples decided they were going to keep having kids until they had a boy. Would that impact the proportion of boys to girls? Well, that's kind of hard to determine analytically. And then it wouldn't be practical to sit there and do it over 20 years to see if these couples actually kept having kids until they got a boy, if that changed the population. So that's where simulation comes in. So to do this, we have to design a method that uses some random mechanism, such as a random number generator or a table, tossing a coin, rolling a die, etc., to represent an observation. And when we do this, we have to be sure that the important characteristics of the actual process are preserved. So if we go back to our example about having kids, so you have a boy. It wouldn't be practical to roll a dice and say there's 6 different options. Now you could roll a dice and an even number versus an odd number, boy or girl. But to sit there and say there's 6 different possibilities, no, there's only 2, boy or girl. So make sure you keep those important characteristics in place. We generate an observation using our method that we determined in step 1 and determine if the outcome of interest has occurred. And then we repeat step 2 a large number of times, at least probably 100 times. We would repeat it. And then calculate the estimated probability by dividing the number of observations of the outcomes of interest by the total number of observations generated. Okay. Let's flip over and look at this example now. So suppose that couples who wanted children were to continue having children until a boy was born. Would this change the proportion of boys in the population? We're going to use simulation to estimate the proportion of boys in the population if couples were to continue having children until a boy was born. So, let's see. Could you go back to... Yeah, sure, Yusuf. Yeah. Let me know when you're ready to go to the next one. You're welcome. Okay. So we're going to use a single random digit to represent a child. If it's an odd digit, then that's a male birth. Even digits represent female births. So we're going to select random digits from a random digit table until a male is selected, and then record the number of boys and girls. And repeat step 2 a large number of times. So I didn't print the table in the notes, I'm sorry. You can try writing it down if you want to, or just follow along. It's up to you. So in our simulation here, remember, we're going to keep having kids until we have a boy. Boys are marked by odd numbers. So for this first trial, what would the 0 be? let's just, well, let me back up. Zeros are even. I should have stated that. Zeros are even. So what would the outcome of our first trial be? Girl, and then the next trial, what would the outcome of that one be? Boy. And we stop because we have a boy. What about the next one? Girl, boy. And then 6, 7 gives us girl, boy. Then next trial, boy, boy, boy. And it looks like we have girl, girl, boy. Trial 9 would be girl, boy. And I feel sorry for this 10th family. Yeah, 6 girls, and then they finally get a boy.
Wait a second. How can you tell like which one is like the family's going to church? I'm confused.
So what we're doing is we start at the beginning of our chart. Girls represent even numbers, boys represent odd numbers. We're going to keep going until we get a boy. So,
and then it goes to the next family?
Then you go to the next family.
Okay, I got you.
Yeah. And so we're not going to sit here and keep doing this forever. Hopefully by now y'all are getting the hang of it. So we would keep doing this until we got about 100 trials in the mix. Then we would need to calculate what's the proportion of boys to overall. So if we did just in 10 trials, we got 10 boys to 22 total. So that's pretty close already to 0.5. It's not exactly 0.5, but we're close with just 10 trials.
Are we supposed to put trials down?
It's up to you.
Okay.
You can, or, I mean, y'all have the random digit table, so the only problem with that would be you don't have the table.
Use this.
Yeah. Okay, so as far as chapter 6 goes, that's it. So AP, y'all are done. There's no homework on 6.7, which means y'all don't have homework this weekend. If y'all want to do the next bit of notes with us, y'all can. If not, y'all can relax. Okay, dual credit. I'm sorry, we've got an extension. Yes.
So basically, we just have to write the trial.
We have to what?
Basically, we just have to write the trial.
Yeah.
That's all there is to this kind of thing.
Uh-huh. Yeah. Okay, so let's move on to permutations and combinations. So our dual credit extension. If you wanted to, maybe on top of your notes, you want to put section 3.4 because that's what these notes go with, is the homework 3.4 that I gave y'all. Okay, so well, let's first back up. So in 6.1, I went in and I touched on what we call the fundamental counting principle. Here we call it the fundamental counting rule. Same concept. So if we had a sequence of n events, the first event had K1 possibilities, second event had K2 possibilities, third K3, and so on. The total number of possibilities of the sequence would be K1 times K2 times K3, all the way to K sub n. So hopefully you remember when we touched on that back in 6.1. And those of y'all that are virtual, I forgot to mention, I uploaded these notes into the test 2 materials folder for dual credit. So if you're wondering where these notes are, check test 2 materials. Okay. So let's first look at factorial notation. So for any counting number n, meaning 1, 2, 3, 4, 5, 6, etc. N factorial would be essentially starting at that number and counting backwards. So if this was like a 6, it'd be 6 times 5 times 4 times 3 times 2 times 1. You start and then count backwards, multiplying the whole way.
So do we not have homework?
Yep, no homework. Okay. I can pick some if you want some. Well, I told our peers just start looking, since we covered a lot, maybe start looking over your notes to get ready for the test.
Yeah.
Okay, so a special note here is that 0 factorial is equal to 1. So let's look at some examples. Hopefully, this is self-explanatory. Nonetheless, let's see some examples of this. Okay, so if we have 4 factorial, we would start at 4 and then just count down. So 4 times 3 times 2 times 1. What would that give you? Yep, 24. Now let's say we had 9 factorial. How would I do that one? That's right. 9, 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Now, I don't know about y'all, but I don't want to sit here and enter all of that into the calculator. Not when I can do a couple of steps and have the calculator calculate it for me. So, in the calculator, you would type non-factorial, but to get the factorial, you'll hit math. And then go over to probability. Like, what is it, PRB? So on your 84s, math, then probability, which is just PRB. And then I think it's option 4. So that's how you get the factorial. And you're like, okay, well, what about the inspire? Well, I'm not going to show you. If you want to figure the inspire out, you can. But I'm just showing the 84 steps because that's what you're going to have to test with, is the 84. So what is 9 factorial? That's right. 362,880. Questions on this one? Okay, let's go back to the PowerPoint for a second. So, for a permutation is an arrangement of n objects in a specific order. The number of different permutations of n distinct objects is n factorial. So if we want to put all n of them in order, we can just do n factorial. But that's if everything was different and we wanted to use all of them. We're going to see some cases, though, where either we don't want to use them all, or they're not all different. So, if they're not all, or let me back up. If we don't want to use them all, so we have n total objects, we only want to take r of them to put in order, we could use the following formula. It's just n factorial over n minus r factorial. And this formula is on your formula sheet, so don't look at it and, oh gosh, I don't know if I can remember that. It's on your formula sheet.
So factorial just means like that number and then times every other number below it.
That's right.
Okay.
That's exactly right.
And what point is there for factorial? Like why would we use it?
So it helps us with permutations and combinations.
Okay.
It'll help us figure out how we can order how many ways we can order things. And
Okay.
it shows up in other applications. I just can't think of them off the top of my head. Okay, so let's actually look at an example at the bottom of that slide. The supposed business owner has a choice of 5 locations in which to establish her business. She decides to rank each location according to certain criteria, such as price, parking, etc. How many different ways can she rank the 5 locations? So we have 5 different locations to rank. Let's first try to reason through this, and then we'll put it in the terms that we talked about. So she's got 5 to rank. 1, 2, 3, 4, 5. How many can she pick for first place, basically?
1.
Well, she can pick one. I should have said how many can she pick from.
Oh, okay.
5, right? How many, so we pick one, he's left to pick from for second place.
4, 3, 2, 1.
3,
Oh, I see.
2, 1. To figure out how many ways, multiply. So this is the same as 5 factorial, which is,
How do you do that?
what's that? 120.
I figured out how to do it.
So math, probability, and then factorial.
Oh, shoot. That's cool.
Questions on this one? Okay, so next one. A radio talk show host can select 3 of 6 special guests for her program. The order of appearance of the guest is important. How many different ways can this be done? So first we're going to reason through this one, then we'll use what we've learned. So how many can she pick?
3.
3.
Yes,
Okay.
6 people.
6 people on the first time, and then 4. Okay, all our spaces are filled, so we can multiply and get our answer. 120 ways, that's right. That's just using logic and reasoning. Now, let's use permutations. So we're going to solve this a different way now. So using permutations. Okay, how many can we pick from? 6. So in our formula that we should have written down, the n is how many we can pick from. So we can pick from 6. How many are we actually picking?
3.
3. So we set our formula. I'm about to mess this up. So that's what it would look like in symbols. The permutation, where we have 6 and we pick 3, is equal to n factorial on top divided by n minus r factorial on bottom. You can certainly type it in like this, but there's an even easier way. So what we can do is you would type 6, and I'm just going to write it, and I'll show you how to get to it, and the 3. So if you did the factorial with this, you're like, wait, that was right above. And you'd be right. So this NPR, you go to math. Then go to probability. And I want to say this is choice 2. Choice 2. And you put this in the calculator, and it would tell you the answer is 120. Let me make a note down here. This is our calculator steps.
Oh, shit, no work. Like, there's gonna be like situations where like that actually is more helpful than the other way. Like when it's like a higher number of combinations you can choose from. Gotcha.
Like if we had, if we're picking 5 people, I mean, you can still reason through it.
Yeah. But like in like a bigger scale thing, like we're picking like 20 out of 100 or something like that. Okay.
Questions on this example, or on how to do it in the calculator? You say you do have a question on how to do it in the calculator? It's not working? Okay, let's take a look. Okay. So we'll want to, first we'll want to take our 6. And then do our steps to get the NPR. So hit math. So we'll look at probability. And then select one we want. And hit enter. And then we need to put our 3. And that same menu, that PRV menu that we went to, is also where you can get the factorials. Okay. Let me go back to our PowerPoint. We did that. Okay, now sometimes we have repeats. So we need to figure out how we can calculate the number of distinguishable permutations. If we've got things that repeat, that's going to be kind of hard to calculate. I'll say it's going to be hard. It's not hard, but you want to remove those repeats because they're not really telling you anything. So, let's look at that. So, essentially what we do is we start off with the number of objects we have, so n. Then we have to divide by however many each one repeats. So let's say 1 repeated 3 times, we would have to put a 3 factorial right here. If R2 repeated 6 times, this would be a 6 factorial, and so on. This you cannot do in your calculator. You can do the factorials, but you can't actually just do like we did on that permutations where you just put in the N and the R and boom, there's your answer. You gotta do a little bit more work on it. Okay, so let's look at an example. How many permutations of the letters can be made from the word statistics? Well, just to kind of set the stage here, if I wrote out statistics like this, and then are those different?
Yes. Wait. Like color-wise, or
Well, either way.
the blue teeth in different place?
Blue tea's in a different place. Now let's say I took the color away from it.
It'd be the same.
They'd be the same, right? So would those be distinguishable from each other
Without color?
without color?
No.
No. So without color, these are the same. So we've got to figure out how many ways can we arrange the letters to where we won't get the same arrangements. So we've got to look at the repeats. There's a more technically correct way to say that, but I just say look at repeats. So what letters repeat in our word here? So how many times does S repeat? 3. How many times does the T repeat?
4, 3, 1,
1, 2, 3. Does the A repeat any? No. We already talked about T. What about I? Twice. We already talked about S, T, I. C, does it have any repeats? No, and then S. Okay. So to figure out the ways you can order it, you have to first get your N. So what's our N? How many letters are in our word here? One, 2, 3, 4, 5, 6, 7, 8, 9. Looks like we have 10 letters in our word. So then on top we would have 10 factorial divided by 3 factorial times 3 factorial times 2 factorial.
You can put that in the calculator, too.
You can put if you just type factorials, yes. Now, I will caution you, make sure you put your denominator in parentheses.
Sorry.
So you would put this in, like if you put it in the calculator, like this. That's how you put that in the calculator.
Is that how you wanted us to do it?
What do you mean?
Is that what we're supposed to do, or is there like another thing to say?
Putting that in the calculator, that's how you can do it. This is really the only way to do this type of problem. And what would you get?
I don't think I got it right. That's supposed to be a big number.
Yeah, it'll be a pretty big number.
I got 16,800.
That sounds right. I'm just double checking from last period so I don't have to enter it again. But I gotta enter it again. Oh, wait, there it is. 16,800. I think we actually might have entered something in wrong. Did anyone else get something other than 16,800? What did you get?
50,000.
50,400 sounds more like it.
What is it?
50,400. Let's
Oh, I see that. Let me try this. I think I did it right, I just put the wrong numbers in. $50,400.
Yep.
Weird, how it does it.
Okay, so questions on permutations. Okay, then let's look at combinations. So a selection of distinct objects without regard to order is called a combination. So the key to remember here, permutation means order matters. Combination means order does not matter. So let's kind of do a little exploratory exercise for a second. So let's say we pick two distinguishable letters. So we're not going to pick the same letter. We're going to pick pairs, but not of the same letter. If we did a permutation using the letters A, B, C, and D, then we would have AB, AC, AD, BA, BC, BD, and so on. In the permutations, AB is different than BA. But in combinations, they're the same, since order does not matter. Good luck tonight.
Thank you, I appreciate it. Want to know?
This is gonna be all black and white.
I'm gonna post the recording when we finish.
Alright.
I'll say when we finish. I'll post it tonight sometime. So it'll be up there. So if duplicates are removed from the list, well, we have AB, which means we can throw out BA. We have CA, which means AC can be thrown out. Since we have BC, we can throw out CB.
My bad. I did not mean to disturb Brad, but sure.
Since we have DA, we can throw out AD. Good luck. And then we just keep going and canceling any that repeat. So we have DB, we don't need BD. And same with DC. We already have CD. We don't need that one. So that means the combinations of A, B, C, and D are AB, CA, DA, BC, DB, and CD.
Mr. Schultz, go on.
Have a good one. So we cut it down from 12 down to 6. Just by removing the duplicates. Let's see, summary. So let's look at our combination formula. So the number of combinations of R objects selected from N objects is denoted by NCR, where the N and the R are subscripts, and is given by the formula N factorial divided by N minus R factorial times R factorial. So it almost looks similar to the permutation formula, except for the fact that we've got to divide out the repeats. So that's where that other R factorial comes in. Okay. Let's look at an example. The number of combinations of 4 objects, if we take them 2 at a time, it would be what? So let's set that up. So how many total objects do we have to pick from? 4. How many are we actually picking? 2. So if we set up our formula to be 4 factorial on top over 4 minus 2 factorial times 2 factorial. It would be 6. Now, there are 6 ways. You can do this in the calculator too. I just say calculator. And it looks really similar to the permutation. So you'll do 4, but instead of saying NPR, it'd be NCR, and then 2. So to get the NCR, you would go to math, probability, and I think it's what, option 3? Y'all said it was 3? Okay. I'll have the menu memorized like I should. Questions on this example? Okay, on to the next one. So at this point, we're just going to be working straight examples. That's the new material. We're just working examples so y'all can get the hang of it. So an advertising executive must select 3 different photographs for an advertising flyer. If she has 10 different photographs that can be used, how many ways can she select 3 of them? So how many total are we picking from? How many are we wanting to pick?
3.
And does order matter? No. Order does not matter. It doesn't tell us that it matters, so order does not matter. Which means this is a combination. So we have 10 C3. If we did it in the formula format, we'd say 10 factorial over 10 minus 3 factorial times 3 factorial, which gives you, yep, that one is 120. If we do it in the calculator format, it would look like that, which is 120. Yes. Questions on that one? Okay. Next one. In a club, there are 9 members. A committee of 4 members must be selected. How many different possibilities are there? Okay, well, how many are we picking from? How many are we picking? And does order matter? No. So this is a combination. We have 9. And the way you actually would read this, I'll say 9, it's not 9C4, you'd say 9 choose 4. So if you wanted to like read it mathematically correct, you'd read that 9 choose 4. Okay, so if we set up our factorial formula, 9 times 4 factorial times 4 factorial. Of course, you can always do this on the calculator. $126. So what are y'all thinking of this? Easy, hard? Easy? Okay, last 3 examples. So those last 2 we knew for sure combination because that's the topic we were on. Now we got to pick combination or permutation and then use the correct one. So it says the company Sect has 10 members on its board of directors. How many different ways can it elect a president, vice president, secretary, and treasurer? So how many do we have to pick from?
10.
10. How many are we picking? 4. Does order matter? Yes, it does, because we're talking about positions here. So order matters, which means permutation. Okay. So what would formula look like if I did it that way? For a permutation. N factorial on top, divided by n minus r factorial. But, of course, you can do it in the calculator, too.
$5,000.
5,040, that's right. Any questions on this one? Okay, now let's look at the next one. Miss Lawson has 12 students in her statistics class. She needs to send a group of 4 students to the Go Center. And how many ways can she pick students to go to the Go Center? Order does not matter. Which means it's a what? Combination. So how many do I have to pick from? And how many am I picking? So set up our formula. Yep. Over. And then 4 factorial. 495? Yep. And of course, if you did this in the calculator, 12 CR4. That's if you, that second part's if you did it in the calculator. Okay, so I want y'all to try the last one and see if you can get it. What'd you get? Yep. Did you get something on that one? And so is it? That's right. Yeah. And so order now there's a bunch of these. Permutation.
Oh.
Which one did you write down? Uh-huh. There you go. Okay, last one. So suppose we were asked to list in order of preference the 3 best movies we've seen this year. And we've seen 12 of them. So we've got a list in order of preference, the top 3. Well, since it says in order of preference, that means permutation, order matters. So we need a permutation. Okay, well, how many do we have to pick from? And we're picking 3. So we want to do a permutation. So we need 12 factorial over 12 minus 3 factorial, which in the calculator is the NPR. And as most of y'all got, it was, what, 1,320. Okay, that's the next. So this goes with 3.4. Assignment 3.4. Recording.